All right, so thank you so much for giving us the opportunity to come speak to you today at the STEM Speaker Series. And so, like Erin mentioned, my name is Connie, and this is Tory over there. And we're both PhD students at Stanford University. And so we also are both coordinators for a science outreach program at Stanford called Science Teaching Through Art, or STAR. And so some of you may have already been at the poster exhibition we held today over at Building 9. And so before we both get into the stories of how we both became scientists, I wanted to just take a few minutes to tell you a little bit more about our outreach program, STAR. And so in addition to Tory and I, there are 3 additional PhD students who helped organize the STAR program this year. And so as you can see, we all come from very different science backgrounds, like ranging from physics to biology and to environment and resources. But the one thing that we all have in common is that we're all very passionate about communicating our research to all types of audiences. And so this is what STAR is all about. So STAR is an entirely student-run program that aims to connect Stanford researchers with the general public through fun educational outreach events. And so as scientists, our group believes that communicating what we do with the general public is really, really important. And so first of all, it helps people understand why our research is important and also how it will impact society. But second of all, it also makes science more accessible to people who aren't directly involved with the work, but who might still be interested in following along to see how the research progresses over time. And so for all of these reasons, our main mission at STAR is to train Stanford scientists to become better communicators about their work to any audience. And so specifically, STAR has been focusing on sharing our research with younger students like yourselves to hopefully get you excited about science and also to allow you to see what kind of STEM career opportunities are available out there. And so to do this, we first have our participants go through a series of communication and art workshops to teach them the skills to explain their research in ways that are very fun, clear, and understandable. And then afterwards, they're going to use the skills that they learned to create infographic posters about their research and go around to different schools in the Bay Area, like local community colleges, just like today, and also local high schools to share their creations with younger students like yourselves. So for those of you who attended our session today, we hope you enjoyed it. And yeah. So with that, thank you so much for giving me some time to just talk a little bit about our outreach program. And so we know that some of you guys might be interested in doing some summer research. And so if you're interested in participating in STAR next year and learn new ways to talk about your research, don't hesitate to let us know. And so feel free to come up to us afterwards to chat with us or contact us by email. And so before I pass it on to Tory, does anyone have any quick questions about this program? Okay, great. So I'm going to pass things over to Tory, and she's going to tell you about her journey to becoming a scientist.
Hi, my name is Tory, as Connie said. So I am a 6-year PhD student at Stanford, and today I'm going to talk to you a little bit about how I got into science and what I value about it. So first I just want to go into a little bit about what I study. I know I saw some of you at my poster session, and so you know I study cholesterol, specifically how we take it in from our food. And I actually work on this protein here that I've drawn as a hand. It grabs cholesterol as it travels through our intestine and helps take it into the body. I also study streptozettamide, which blocks that function. We actually have very little knowledge about how the drug and the protein work, and so I'm trying to figure out how those work. So I'd like to go into how I got into science. I know it's a little bit unusual for a person in their 50s to still be in school. And I guess I am unusual in the fact that I absolutely love school. I've been going for a great deal of my life. But I do understand it's not for everybody. Not everybody has a relationship with college. And I have 2 kids in college. Both of them, I have to say, went rather reluctantly. And so we had many discussions at home, whether or not college education is really worth it. So that's what I'd like to ask you. You are college students. And I'm sure one thing that you have all seen yourselves is how expensive college has gotten. You can see that tuition has risen far greater than the consumer price index. It's just totally outpacing the inflation. And so there was actually an article published in 2013 in the Wall Street Journal. And unfortunately, this guy decided, after looking at the figures that a college education education is no longer worth it, which is really quite troubling. So a lot of people readdressed this data and took another look at that. So I want to talk about some of those other researchers and what they found looking at college education. So there was a great article that came out from the Federal Reserve Bank of New York, and by these two authors, and they looked at the cost of college versus future wages. So at least this is the cost of college, and yeah, absolutely, it's gone way up. The dotted lines are actually what the tuition costs are represented to be, but they're not taking into account a lot of the discounts that people get. There's grants, there's scholarships, there's tax benefits. So these solid lines actually represent what the real costs are. But there's another cost that they needed to take into account. So when you're going to college full time, you're missing out on lost wages. They call that opportunity cost. So they combine those two to get the cost of an associate's degree or a bachelor's degree. Now we want to look at what do you get for getting a college degree. Well, there's two sets of earnings here. One is from the Pew Foundation, and the other one is from the article. And you can see that a bachelor's degree actually earns quite a bit more than an associate's degree, and quite a bit more than a high school diploma. So they combined these two sets of data to look at the return on your investment for a college education. And in fact, it's very good. You get about a 15% average return on college education. Now, if you look at the return on stocks since 1950, that's only 7%. Bonds, only 3%. You're getting 15% for a college education, whether it's a bachelor's degree or an associate's degree. But I do want to point out here, if you look at the top, you're actually getting above 15% if you're in some of those STEM majors. So what you major in actually does make a difference, and it's not just for a bachelor's degree. This is from another report from the Wall Street Journal. This one had a more favorable view of college, and there's a number of degrees you can get at an associate's level that actually outpace the average bachelor's degrees. So I would say yes, from a financial standpoint, college is still definitely worth it. If it's an AA or a bachelor's degree, it's a good investment. But the other question I want to ask, is money the only measure of worth of a college education? So what I'm going to do now is tell you about my personal journey through college and how I got to science. So in 1980, I went to a small liberal arts college in Vermont called Middlebury College, and actually got a bachelor's in art history. From there, I went to the University of Southern California, and I got a master's in fine arts and filmmaking, and I studied animation there. But I'll be honest with you, it was really hard to make ends meet with these degrees. And so, sort of just by a strange twist of fate, I got involved in produce, and I started my own wholesale produce company. I've been doing that for about 25 years, and I still do it on the side to help pay for some of my bills. But while I was doing that and raising kids, I went to all sorts of adult ed classes because, like I said, I love learning. But I wanted more of a science background, so 10 years ago, I went to San Jose State University. I loved it there. I went through their biochemistry program. And then I finally ended up at Stanford. I'm in the Department of Biochemistry, just a few months away from earning my PhD. So one thing that people have asked me, especially my kids, was, why did you get a degree in art history? Did you feel it was a waste? Don't you wish you'd gone into science from the very beginning? And my answer is absolutely not. I value every class I've ever taken. My life is far richer, more interesting for everything that I've learned. I am better at problem solving, I'm more creative, I think I'm a more tolerant person for all the education that I've had. But given this is a STEM talk, I am going to focus on what I've learned in science and why I particularly value the education that I've gotten in science. So I have been able to do really amazing things while at Stanford. I've gotten to play with radioactive chemicals, I've gotten to stain cells, different colors, and look at them in a microscope. I've gotten to manipulate DNA and put mutations in different proteins. But what I value more than anything else from a scientific education is that it teaches critical thinking. And as you go through your STEM classes, you're going to learn all sorts of amazing things, but I promise you, you're not going to remember all of it. You're going to forget some of the facts and the formulas. What I really hope that you try to take away from this and be mindful of this as you go through your classes is try to develop your critical thinking skills, because those are going to help you in all areas of life, and it's the most important thing I think you get out of a science education. So what I'd like to do for the rest of my talk is go through some of the steps of critical thinking, and we'll work on this together, and hopefully I'll get some feedback from you guys. So let's revisit this graph I showed you from the very beginning. This was put together to prove a point. He wanted to show that college education is no longer worth it. And I would say this graph, is somewhat convincing. But let's look at this. Okay, so the blue line represents tuition plus room and board. Well, you're going to pay to live somewhere and to eat whether or not you're in
college, right? So to include the room and board in there is not really fair. I think tuition is fair, but not room and board. Also, the blue line represents 4 years of college, and the red line represents the average annual salary. So you've got kind of a 4-year difference there. You're comparing apples and oranges. I don't think this is a really fair graph, and I don't think it does a good job, but this is a good example of somebody trying to, I don't want to say manipulate the data, but present things in a way that's going to make you believe their point. So let's go through a few graphs here, and I want to get some feedback from you as to what you think might be wrong with these graphs or what your impression is. So in 2005, Florida had this stand your ground law. This shows the gun deaths in Florida after this law was put into action. What do you take away from this, or what is wrong with this? Somebody want to give me some feedback here? So it looks like the number of deaths went down and then went back up, right? That's exactly what they want you to think. But, yes?
It's lower at the top and the scale increases as it goes
That's
down.
right. We always expect to have 0 down here. That's where it typically is. They switch the y-axis, right? So how deceiving is that? Let's look at another graph about interest rates, right? So this one looks like interest rates have drastically increased from 2008 to 2012. Who wants to comment on this one? What's that? Somebody raise your hand. Okay, yeah.
The y-axis is really, really small.
That's right. They don't start at 0. They have shrunken it way down to exaggerate the point here. But if we fix the y-axis, you can see there's hardly any change at all in interest rates. All right? So this was something that was actually tweeted by the National Review, a very conservative magazine and journal, and they don't believe in global warming. And so this was the graph that they presented and said the only climate change chart you need to see. Who wants to comment on this one? Yeah.
The range of useful data is so minuscule compared to the whole station.
Exactly, right. So it doesn't look like the temperature is warming here, but really what we want is the change in temperature, not just the annual temperature. And so this is reworked data from NASA scientists. You can see, yeah, it's changing every year and it's going up, and global warming is something we need to be concerned about. So I'm going to give you one last example here. This is completely hypothetical. But let's say you wanted to get a dog, and there's only 3 dogs possible on the planet, right? And you're concerned about biting. So you want to know what kind of dog is the biggest biter, right? So this is, you find this graph, okay, so we see that the red and green are almost the same, but that blue dog bites quite a bit. What other information do we need to make a good decision here? Anybody have any ideas? Well, you might assume that maybe they all represent 33% of the population, right? But maybe they don't. If you look at this, you can see actually this crazy red dog is a very small percentage of the population, but one of the big biters. And so you might want to avoid it there, that dog. But in this case, percentages can be very useful, but numbers would actually be good here too. What if there are 30 million dogs and in an entire year you only get 100 bites? Well, the incidence of biting is so low, in fact, you don't even have to worry about what kind of dog you get. So now I'm going to bring you to a real-life graph. This was published in 1999 by a Dr. Andrew Wakefield in The Lancet, which is a very well-regarded medical journal in England. And he claimed that there was that getting the MMR vaccination caused autism. And so what he's showing here, or claimed to be, was this is the increase in autism. This is where the MMR started to be given in California and in Great Britain. And this caused this huge anti-vaccine movement. And I'm not going to go into everything that's wrong with this graph. This guy has been discredited. He was also paid $650,000 by lawyers who were suing the MMR manufacturers. So we had a huge conflict of interest here. But one of the things that's really important that you have to look at here is that correlation is not causation. So that's something that comes up all the time. If that were the case, then we might also say that organic food sales could have caused autism. They're going up at the same rate. Now, obviously, that's not true. But let's say you were a parent and you were concerned about this and you're considering, am I going to vaccinate my child? Well, let's educate ourselves and pretend we're in that situation. First of all, is autism really on the rise? Well, there are people who say, yes, absolutely it is, and I agree with that it is. But what is the cause of that? Is it the vaccination? I think part of the reason, and I think this is well agreed upon, is that we have different ways of diagnosing it, and we've expanded the set of behaviors that are included in autism. And so partly it's just better diagnoses that has given the rise in autism. But I think there are also environmental factors that we haven't pinned down yet. Is it vaccination? I think that's been proven that it's not, but let's say you didn't know, and you wanted to know, gosh, are measles, really that scary? Is it worth it to vaccinate my child? Well, I'm going to show you a little video here just to educate ourselves here on measles. It's by this group down here, and one of the reasons why I want to show it is not just to let you know a little bit about measles, but these are fantastic people here. They do a great job of presenting science through art, and so this is definitely something up our alley. So let me get to that.
Recently, there's been a lot of talk about measles. What does measles actually do, and should you vaccinate against it, or is this just hysteria? Measles is a virus, a hull of proteins, RNA, plus some more proteins for reproduction. It cannot reproduce by itself, it needs a host cell to do so. To understand measles, we have to understand the immune system. You might already have seen the visual system we developed to help here. Now, let's focus on the parts of the immune system relevant to measles. The measles virus enters humans through the nose, mouth, or eyes. The measles infection starts in the lungs. Measles is especially good at infecting the body's first line of defense, macrophages, powerful guard cells that protect the lungs from intruders. They enter a cell and take it over. The virus reprograms the cell and transforms it into a dangerous virus production center. Once a cell is filled with viruses, they leave the crippled cell and begin the cycle over again. But the immune system has powerful weapons against virus infections, natural killer cells. These cells basically patrol the body and check other cells for infections. If they find an infected cell, they order it to commit suicide. This is so effective that for the first 10 days or so, you will not even notice that you're infected with measles. And now, the reason why measles is so powerful. After a period of fighting and dying, macrophages alert the brain of the immune system, the dendritic cells. The job of the dendritic cells is to collect samples of intruders, travel to the lymph nodes, and then activate the heavy weapons that eradicate the infection very fast in a team effort. But the measles virus uses a dreadful tactic. It infects the dendritic cells and uses them as a Trojan horse to enter deeper into the body. The infected cells travel to the next lymph node to alert other immune cells. Once it arrives, the measles virus spreads around the virgin T and B cells and infects them. It attacks the very system that evolved to fight it. Now, things happen very fast. The lymph system spreads the virus everywhere and it enters the bloodstream, infecting cells while traveling. Measles infects organs like the spleen, the liver, the intestines, and most importantly, the lungs. The symptoms range from a very high fever, headache, sickness, bronchitis, and of course, a rash. In the lungs, the immune system was doing pretty okay, but now millions of viruses attack a second time and kill countless cells, wiping out the defense systems. In this phase, you start coughing out millions of measles viruses. Measles is so contagious at this stage that if you meet someone who isn't vaccinated, there's about a 90% chance you'll infect them. Without a protective army in the lungs, other bacteria or viruses that would usually not stand a chance can now enter the lungs and develop into harmful parallel infections that can cause pneumonia, the most common way to die from measles. Your body's immune system is now seriously wounded. Various protective systems are hurt and disrupted. The virus spreads everywhere, infecting the skin all over the body. The typical measles rash now becomes visible. And in some cases, the measles virus reaches the brain and causes a brain infection. If it does so, the chances of dying are between 20 to 40%, and there may be long-term damage. But your body is far from giving up at this stage, and it fights back aggressively. Some dendritic cells survive long enough to activate the antivirus forces of the body. Plasma cells in the lymph nodes
Stop this because I just know the guy lives, but not everybody does. So
I think from this, hopefully, you take away from it that measles is in fact something that's quite serious. Oops, sorry, not. There we go. That measles is something that's quite serious. It's not just a cold, and so if you were considering vaccinating or not, it's something you would definitely want to consider because it's quite a serious disease. But there was a lot of work that was done looking at the link between autism and vaccinations. There was absolutely no link found at all, but still there's this huge anti-vaccination movement going, and it was really fueled by the media. And I think one of the things that's very important to do, being a critical thinker, is look at your sources. So one of the big proponents of this anti-vaccination movement in the United States was Jenny McCarthy, a former Playboy bunny. And she had a child in 2005 that was diagnosed with autism. And she was out there saying that vaccines are not safe. And Oprah Winfrey had her on her show. Everybody loves Oprah and listens to Oprah. And she said that Jenny has mommy instinct and she knows what she's talking about. And so there was a lot of parents that stopped vaccinating their children, not just for MMR. And I want to point out that it was the combined vaccine that was originally questioned, not vaccines in general, but people weren't listening to the experts. They just caught this big wave of anti-vaccination and stopped vaccinating their children. And so Julie Robotham put it very well when she said that Jenny McCarthy demonstrated the superior power of a photogenic individual with a wrenching personal story over painstakingly gathered epidemiological evidence to sway popular opinion. And I'd like to say we're all guilty of that. It's very easy to be swayed by the media, and that's something you have to be very careful not to let happen. And so in this anti-vaccine, I just want to point out a couple of pitfalls that we really all fall prey to. So one is on the left here, this confirmation bias. It's very easy to look at information that points your viewpoint and to just ignore stuff that counteracts it or contradicts it. So really be sure to look at everything before you come to conclusions. Also, this correlation that I talked about before, that correlation does not equal causation, and so be very careful of that as well. Unfortunately, measles cases have dramatically increased in the United States. At the end of 2014, there was an outbreak that started in Disneyland, and it spread to over 100 people and across the country. And so I'm going to end with this comic that shows that the anti-vaxxers are actually goofier than goofy. And so I want to remind you that you actually have an opportunity coming up to be critical thinkers, and I urge you to go out and vote on Tuesday, but to please review all of the issues and the candidates. Don't be swayed by the media or your friends. Do your own thinking and look at your sources. And so I will end this with a quote from the scientist Stephen Jay Gould, who said, "When people learn no tools of judgment and merely follow their hopes, the seeds of political manipulation are sown." So keep that in mind and vote wisely on Tuesday. Thank you.
Hello. All right. Sorry everyone for the delay. So hi again. So once again, I'd like to thank you so much for giving me the opportunity to speak to all of you today. And so as I mentioned before, my name is Connie, and I'm a fifth-year PhD student at Stanford in the Microbiology and Immunology department. And so today I'm going to start off by telling you a little bit about what I do as a PhD student, and then I'm going to segue into a very brief story about a fascinating organism that I studied called Helicobacter pylori, which lives in possibly the harshest environment in the human body. And so I'll let you think about what that environment is for the time being, and later you can see if you guess correctly. And so finally, I'm going to go back in time, and I'm going to tell you about how storytelling brought me into the world of science and how it continues to motivate me to continue doing what I do every day. And so first of all, I'd like to start off with a very quick introduction to what I actually do. And so as I mentioned before, I'm a graduate student at Stanford, and I'm working on towards getting my PhD. And so a PhD program is something that you can apply for after you graduate from college. And what this program actually allows you to do is to get further advanced training to become a better scientist. And so as a PhD student in the Microbiology and Immunology department, I study these tiny organisms called microbes. So how many of you here in the audience have actually heard of microbes and know what they are? Yes, so there's actually plenty of you, great. But for those of you who don't know what microbes are, they're actually these very, very small organisms that can be found practically living anywhere on Earth. And so most of them are actually really good for us in our ecosystems, but some of them can infect us and cause really terrible diseases. So for example, many of you have probably heard about the E. coli outbreaks at Chipotle, right? And so E. coli is a bacterium And a very specific type of E. coli causes the really bad food poisoning that we saw with Chipotle. And so personally, I am very, very interested in the microbes that cause really bad diseases in humans. And one of my biggest goals as a scientist is I want to make discoveries that will help us figure out how to destroy these germs and prevent people from getting sick and dying. And so to achieve that goal, I actually do a lot of experiments in the lab, and that's pretty much what I do every day as a PhD student. I do experiments in the lab to learn about how these microbes live and survive inside the hosts that they infect. And so because microbes are so small, we can't actually see them with our naked eye. And so one of the tools I use very often in the lab is a microscope. So I've shown in the top left image there. And what this tool allows me to do is actually to magnify these microbes and see what they're actually doing. And so currently at Stanford, I'm studying this very fascinating bacterium called Helicobacter pylori. And so it's this little spiral-shaped guy here. It's actually pretty cute. And it has these little tails called flagella that help it swim super fast. And so H. pylori is a really cool organism in many ways. So one thing is that it's a very successful microbe. And so half the people in the world are actually infected with this bacterium. So that's 1 in 2 people has H. pylori. So that's pretty incredible. And so second of all, H. pylori lives in possibly the harshest environment in the human body. So can anybody guess what that is? Absolutely, yes. So H. pylori lives in the stomach, which is basically this vat of acid and digestive enzymes that are designed to break down anything that comes into the organs, such as the food you eat and also potentially microbes that you ingest. And so how do people actually get infected with H. pylori in the first place? Well, first of all, people typically acquire H. pylori when they're kids. And once you get infected with H. pylori, it'll stay in your stomach for life. But fortunately, most of the people who are infected remain healthy and they actually never get sick. But unfortunately, a very small percentage of infected people can develop more serious diseases. So for example, 14% of infected people can actually develop ulcers, which is basically a hole in your stomach. And so that can be really painful. And so on the other hand, 1% of infected people can also develop stomach cancer, which is one of the leading causes of cancer-related deaths worldwide. And so in order to cause disease, H. pylori needs to be able to survive for a really, really long time inside the human stomach. And so my goal as a researcher is to figure out how H. pylori actually lives in such a harsh environment and hopefully make discoveries that can inform us on how to develop new treatments to prevent infected people from developing these diseases. And so right now I'd like you to take a moment and imagine that you're a little H. pylori bacterium and you're getting swallowed by this human over here. And so what do you think your journey down to the stomach would be like? Right, so once you get swallowed, you're going to fall down a deep, dark abyss that's the throat and the esophagus. And after what seems like forever for a tiny little guy like a bacterium, what happens is you fall into this sizzling, burning acid bath here. And so if you were H. pylori, what are you going to do next? Swim. Yes, exactly. I'm going to get out of there. And so to really understand how H. pylori survives in the stomach, I would like to kind of introduce you to a little bit about what the stomach actually looks like. And so the lumen of your stomach is filled with this acid to help you digest food, right? But underneath all of that acid are your stomach cells, shown here in gray. And your stomach cells are actually organized into these really cool folded structures called glands. And so they kind of look a little bit like cave openings. And so in order to protect your stomach cells from being eaten away by the acid, what your stomach actually does is it produces this thick, goopy layer of mucus that forms a barrier between the acid and your own cells. And so the areas of your stomach where the mucus and the cells are actually not acidic at all. And so when H. pylori initially comes into the stomach and falls into the acid, it's probably getting a little stressed out because it actually really, really hates acid. But using its little tails, it actually swims very quickly out of the acidic lumen into these regions of the stomach where it's no longer acidic and it can happily survive. And so here, the bacteria will either stay swimming in our protective mucus layer, or they'll actually directly attach to our stomach cells very deep in the glands, and they grow and divide there. And so these bacteria are really smart, right? They took advantage of ways that our body uses to protect our own cells from the acid, to shield themselves from the acid as well. And so our lab previously found that the ability to get down into this niche deep in the glands is actually very important for the bacteria to survive for a very long time in the stomach. And so now what I'm interested in studying is what kind of factors do the bacteria actually need in order to live down here in the glands? And so if we can figure out what is important for the bacteria to live here, then we can potentially design find ways to kick them out of these glands and prevent them from causing disease. And so that was just a really quick overview of what I do. And so if you're interested in learning more details about my project, feel free to come up to me to chat after the talk. But I'm going to segue into the next part of my talk now. And so I really love my job as a scientist. I think it's so much fun to do experiments and discover new things every day. And I feel so incredibly lucky to be able to do science at a place as amazing as Stanford. But how did I actually end up becoming a scientist? So at what point in my life did I realize that I wanted to do research as a career? And so in the spirit of the title of my talk, I'm going to tell you several small stories that document the different stages of my journey to becoming a scientist. And the first thing I wanted to start off with is my family, because so much of who I am today is due to my family's history and background. And so my grandparents, from both my dad and my mom's sides of the family, were born in a province in China called Canton. And they were living a pretty happy life there until the Japanese troops invaded China in the late 1930s, and a few years later, World War II started. And so because of the ongoing wars, life got pretty hard, and so my grandparents decided to escape south and settled in southern Vietnam in a city called Saigon, which is now known as Ho Chi Minh City today. And so in Vietnam, my grandparents met each other, they got married, and they had my parents. And so interestingly, even though my parents were born and raised in the same city, they actually never met each other when they were in Vietnam. So unfortunately, disaster struck again as the Vietnam War began, and again, life got really hard for my families from both of my parents' sides. And so in 1979, my parents, who at this point have still never met each other, decided to escape over to the US to seek a better life. And so at the time, they were about 18, 19 years old, so pretty much the same age as most of you guys are right now. And so when my parents came over to the US, they both ended up in Southern California, specifically in Orange County, which is just south of LA County, and it's highlighted here in red. And so most of you probably know Orange County as the place where Disneyland is probably. And so after getting settled in Orange County, both my parents found part-time jobs and they were taking courses at a local community college called Santa Ana College. And this is actually where they met for the first time, despite being born and raised in the same city in Vietnam for most of their lives. But unfortunately, a year or so into taking their classes, they had to make a very difficult decision of quitting school to focus on working full-time because they needed to make enough money to financially support themselves and also their families who were still back in Vietnam. And so at the same time, they're trying to bring the rest of their families over to the US as well. And so my mom ended up finding a job with the post office, and my dad started working as a machinist for a control valve company where he helps design and manufacture valves for machines that are used in power plants and oil and gas fields. And believe it or not, 30 years later, they're still working in the same jobs today, so that's pretty incredible. But in 1988, my parents decided to get married, and after that, they had me and my two younger sisters, and we all grew up in the suburbs in Orange County. And so as I was growing up, my parents always emphasized to me how important education was because they never had the opportunity to finish college, and they wanted me to have what they were unable to attain. And so during my childhood, they would always encourage me to read stories and watch TV to learn about a whole bunch of interesting things. And so I remember that one of my favorite books that they bought for me is this one called Hungry, Hungry Sharks, which was about all these different types of sharks and how they lived in the oceans. And so you would think that sharks would be a bit of a scary thing to a young child, but I actually thought they were pretty cool. And as for TV shows, one of the most memorable ones from my childhood was The Magic School Bus. So how many of you guys actually have heard of that show before? Oh wow, so there's actually a lot of you. I thought that most of you might have been too young to have actually watched it, but that's awesome. But anyhow, yeah, it was this crazy show about a teacher who takes her students on field trips in this magic school bus to all these crazy places like outer space or inside their classmate's body when he was sick or to an anthill. And so on each of these field trips, the teacher would explain to her students how things worked in these places, and I just had so much fun watching this and learning about all these random things. And so all these stories and TV shows in my childhood really helped foster my curiosity and my imagination, and I remember thinking, man, it would be so cool if I could grow up and have a job where I could just learn about cool new things all the time, like these kids in the Magic School Bus. But I didn't know that such a career actually existed until 5th grade, when I learned for the first time what science actually was from my teacher, Mrs. Cole. And so there were two aha moments in my time in 5th grade that really set me on the path to becoming a scientist. And so the first moment was, I remember one day Mrs. Cole was telling the class a story about this really famous female scientist named Marie Curie, as some of you have probably heard of her. And so one of the things that Marie Curie was really interested in was radioactivity, which was actually a pretty new idea during her time. Not much was actually known about it. And so through her experiments, she discovered 2 completely new radioactive elements that were added to the periodic table. And I remember thinking that, wow, there's a job where people can actually discover things that no one knew about before. That is so awesome. I want to do that when I grow up. And so the second aha moment was kind of when Mrs. Cole split the class into groups, and she gave each group a battery, a light bulb, and a wire. And she told us, okay, you guys, try to use these materials to light up the light bulb. And so before that, all she really explained to us was a bit about how circuits worked, but she didn't give us any specific instructions on how to get the light bulb to light up. And so I remember my group trying all these different ways and getting really frustrated that things wouldn't work, because this was probably the first time for all of us that a teacher gave us a task and just didn't tell us how to do it. And so finally, after many tries, we finally got it to work, and I remember how empowering and satisfying it felt to figure something out all on our own. And so I didn't know it at the time, but this experience was probably the first science experiment I ever did. And so this is exactly what science is all about, right? You have a question that you're trying to answer, but nobody is going to tell you how to solve it. So you have to figure it out all on your own. And it's very likely that it's going to take multiple failures before you finally get things to work. But when things do work and you make a really cool new discovery, then the feeling is just so great. And I think this feeling of discovery is what motivates scientists, certainly myself, to keep doing what we're doing. And so I realized in 5th grade that I wanted to be a scientist when I grew up. But I didn't actually know what kind of scientist I wanted to become until I took an AP biology class in high school. And so this class introduced me to microbiology, which is the study of microbes, and I completely fell in love with the subject. And so as I mentioned to you before, microbes are these incredibly small, single-celled organisms. And so to give you an idea of how tiny they are, I have a ruler up here on the screen. And so the purple line shows you the length of 1 centimeter, and the red line shows you the length of 1 millimeter, which is the smallest unit you can find on a typical ruler. And so if you were to lay a whole bunch of bacteria right next to each other side by side, it would take 1,000 bacteria to cover the length of 1 millimeter. So these guys are super, super small. And so I just thought that, wow, these organisms are so small and complex, so small and simple, and yet they're able to infect and survive inside something as complex as humans and make us sick or even kill us. And I thought that that was just so fascinating. And so after I graduated from high school, I realized that there was so much more that I had wanted to learn about microbes, and so I decided to major in microbiology at UCLA to continue pursuing my interests in college. And so in my second year of college, I decided that I wanted to start working in a lab to begin training as a scientist, and also to see what doing research was really like. And so I ended up joining Dr. Peter Bradley's lab at UCLA, and I was being mentored by a PhD student in the lab at the time named Josh. And so Peter's lab works on this parasite called toxoplasma, which is found in about 1/3 of the world's population. And they're typically encased in these cysts that form in the muscle and the brain tissue. So it's very possible that about 1/3 of us right now in the room actually have these parasites sitting inside our brain. And so typically toxo is actually pretty harmless. It just kind of hangs around in our brain and our muscle and doesn't really do anything. But we study toxo because it can cause really severe brain damage and eye damage in people who have weakened immune systems, and they can also cause severe birth defects in babies. And so one of the really interesting things about this parasite is that it has to get inside a human cell in order to survive and divide, and if not, the parasites would just die. And so one of the questions that I was interested in answering is, well, what kind of parasite factors does toxo need to get inside human cells? And so at the time, our lab suspected that, this factor that toxo makes, let's just call it factor X, labeled here in purple, and we thought that factor X might be important for invading into those cells, but nobody really studied it before. And so I decided to try to figure this question out. So I thought that if I can somehow make a version of the parasite that cannot produce factor X, maybe I could throw these parasites on human cells and see if they actually have trouble invading. And so I think that this would be pretty straightforward and easy. It sounds pretty straightforward in theory, but I actually ended up trying multiple different methods to try to stop the parasite from making factor X, and actually nothing would work. And so months went by, and I just got extremely frustrated. But Josh, my mentor, actually encouraged me to keep trying and to not give up, even with all the difficulties. And one day, miraculously, I finally got it to work, and it just felt so satisfying. And so after I got it to work, I threw these parasites that can't make factor X onto cells, and I discovered that indeed, if they don't make factor X, they can't invade inside human cells. And so I was really thankful for this experience in the Bradley Lab because not only was I able to learn how to do science with really, really amazing and supportive mentors, but it also gave me a reality check that science is actually a really slow and non-trivial process. So not everything you do is going to work, and the failures can be really discouraging and frustrating sometimes. But these difficulties actually didn't steer me away from science. In fact, I actually loved the challenges and the critical thinking that was required to solve these problems, and I got to discover things that no one had known before, which was something that I wanted to do ever since I was a kid. And so my experience in the Bradley Lab really gave me confidence that I wanted to continue doing science for the rest of my life. And so, after I graduated from UCLA, I decided to apply for a PhD program at Stanford to continue my training as a scientist in the microbiology and immunology department. And so at Stanford, I ended up joining the lab of Dr. Manuel Anieva, who, in addition to the people I've mentioned before, is one of the most influential mentors that I've had in my life. And so Manuel is a really brilliant scientist, and he's so creative, and I've learned so much about doing science from him. But one of the most important things that I've learned from Manuel is how to give a good presentation and how to tell an interesting story about my research. And this is a really useful skill to have regardless of what field of study you're in, even outside of science. And so I remember that Manuel once told me that the best science talks are not the ones where the presenter uses big terms and tries to sound really smart in front of his audience, but in fact the best talks are the ones where the presenter talks about the research as if they're telling the story to a really excited 8-year-old kid. And that really stuck with me because I think that he's right. Like, people like stories. They want to have a character. They want to have a character that they can root for. They want to see the character go through a problem, and they want to see how the character ends up solving the problem in the end. And so one of the really amazing things that I recently discovered about Manuel was that after he graduated from college, he actually went back to Mexico for a few years, and he wrote children's books to teach kids about different science topics in fun ways. And so the books center around this kid over here who meets a gnome, and the gnome actually takes him on a whole bunch of different science adventures. And so in this particular story, this kid and the gnome shrunk to a really small size, and they went inside a leaf, and they're exploring all these crazy structures that they see inside the plant. And so Manuel actually had these illustrations made to go along with his stories, and they're really based on how the real structures look like inside leaves. And so this is an image that Manuel actually took himself with an electron microscope of the inside of a leaf. And if you can see, it actually looks pretty similar to the illustrations he had made for his stories. And so one day, I remember Manuel and I randomly found some audio recordings of his books uploaded onto YouTube. And so we were just spending a lot of time watching them and reading through all the comments to see what people were saying. And so actually a majority of the comments were saying how Manuel's books were actually really fond childhood memories of theirs and that their stories have inspired them so much. And so I just screenshotted one of them. And so this is in Spanish, but basically what it says is, "Oh, thank you. After years of tracking this over the internet, I can finally regain some of my childhood and a giant piece of what made me the way I am. Thank you so much." And so it was really amazing to see this because it totally reminded me of how stories fostered my own curiosity and impacted my decision to go into science. And so everything just kind of went full circle for me, which is kind of crazy. But from this, I was really able to appreciate how stories have reaches far beyond just educating us. They can also inspire us as well. And so because of how stories have had such a huge impact on my path to science, I decided to participate in the STAR program last year to learn how to use storytelling and design skills to make an infographic about my research and that I can share with younger students like yourselves to hopefully teach you guys something about H. pylori, but also to get you excited about science and research. And so after going through the program as a participant last year, I decided to stay on and coordinate the program this year to help other researchers learn these skills so they can also educate and inspire younger students about science. And so my path to science was a really long and fruitful one, and throughout my journey I've learned so many different things. And so the first thing I learned is that it's really important to find mentors who inspire you and support you in your endeavors. And so my parents taught me to be curious, which was really, really important, but they didn't actually know much about science and what research careers are like. And so I was also a first-generation college student, and I was the first one in my family to actually pursue anything related to science. And so if it weren't for my 5th grade teacher and my other science mentors, I never would have been able to become a scientist. And so the second thing I learned is that no matter what field you're in, storytelling is not only important for educating people, but also for inspiring other people. And so people love stories, so use them to get people excited about what you're passionate about. But like Tory also mentioned, storytelling can also be a very dangerous tool if used inappropriately. But the next thing I learned is I think it's really important to find a career that's able to foster your curiosity and your imagination, because that will really give you the motivation to keep doing your job. And so I feel so lucky to be able to do what I love every day, and also to work alongside people who are brilliant and inspire me to be better all the time. And finally, I've learned not to be afraid of challenges and failures, because you can learn as much from them as you could from your successes. And also don't be afraid to try things out just to see if you like it, because you're never going to know until you do it. And so hopefully you can relate to some of these experiences that I've shared with you today and find some of these ideas actually helpful for your own journey in discovering what you want to do. And so with that, I'd like to thank everyone who has been with me throughout my path to science. And so all the mentors that I mentioned throughout the talk for encouraging me to be a scientist, my parents for teaching me to always stay curious and always supporting my choice to become a scientist, even though they didn't really know what research was like. And so my lab members and people in my department for all their support, the STAR program for letting me merge my love for science, storytelling, and art together. Kenyatta College, especially Kathy and Aaron, for giving me the opportunity to speak here. And finally, my funding sources for providing me with the resources to do my research and my job. And so with that, I'd be happy to answer any questions you may have about anything I talked about today.